One thing that I would like to add to this discussion is that what causes the laser line width to broaden? I mean, we all know that it's not going to be a delta function, but what factors determine the width of that laser line width? So, and those factors prevent it from being, of course, a very sharp delta function like profile, but also those factors contribute to the broadening. So what I want to discuss here is that what are the factors that contribute to the broadening of the laser line width delta nu L. Okay, and and we will discuss these in detail later. So I should mention here that, so this is the question, and the answer is that these factors called line broadening mechanisms will be discussed later, but some are introduced here. So the point is that some of these are pretty technical sort of factors. I mean, just because the mirrors jitter and there may be impurities or something, and that can cause a broadening. But the more interesting ones, so for example, in gas lasers, okay, in gas lasers, the atoms of the gas move around, and owing to that, there is Doppler broadening. Now, exactly how the Doppler broadening of the gas, quantitatively, how that transfers over to the line width of the laser, we will discuss that later. Okay, so there's Doppler broadening. Then I'm trying to think of other examples. In gas lasers also you have so that's one. Okay. Also pressure in gas leads to pressure broadening, and this is due to collisions. Pressure broadening, also called collisional broadening. And once again, how quantitatively we can work that out later. Okay, so these are examples of in gas. I'm trying to think of, and then of course in diode lasers, yeah, that would be a good one to look at. In diode lasers, you can have, what we'll see is that there can be basically in diode lasers and also solid state lasers. Okay. So diode lasers, I mean the ones you're using have indium, gallium sort of substrates, active media inside. Solid state lasers are the titanium sapphire lasers we've discussed in the past, the neodymium YAG lasers. So in both of these, what happens is that there can be non-uniformity of the gain medium. So for example, in the diode laser, you can have, we'll discuss, I guess, well, okay, so maybe I can discuss it now, that what the diode laser actually looks like is that there is an active medium. So let's say that, let's say that the medium or the chip where the lasing actually happens is this narrow, and usually it's long in one dimension and short in the other. And so this is your gain medium, okay, and so it has some sort of material inside, usually some, I'm forgetting the exact combination right now, with gallium aluminum arsenide or something like that, and there's some indium and stuff, and it's just a few microns in width this way, and the other way it might be like 10 to 20 microns, something like that. Okay, so that's typically what it might be like. And the gain medium, and so this is your actual, and the gain medium is some kind of semiconductor. Okay, on either side of the gain medium there are some extra layers. Okay, so extra layers, for mechanical support. Okay, and so this is also called, also known as the cladding sometimes. Okay, just for mechanical support. And then finally there is something surrounding that too. Okay, and so this is some extra substrate, okay, just for mechanical, even more mechanical support, doesn't really matter. But the point is that on this mechanical support, then there's terminals, okay, and so this would be the plus terminal, and here, so these are where those pins that you saw in the diode laser go, okay, and minus, okay, and so there's an electron flow from the minus to the plus, right? So there's this electron flow, so you pass this current, okay, from one to the other, and then if we have time, then we will discuss this later, that how is light actually produced. Well, so it's a semiconductor, there's a semiconductor junction in there, so-called PN junction, and so light is produced by something called radiative recombination. If we have time, we'll discuss this, of electrons and holes at the PN junction. Okay, so again, we'll discuss this later. We'll discuss later. The key point is that you need the electron density determines how efficiently light is being converted or produced. Okay, so efficiency of light production on the electron density. Okay, so this electron density is not uniform everywhere, because as you can sort of guess, that if you have a current going, electrons flowing like this, then there's a certain profile to this electron flow. It might be more in the center and then falling away as you move radially outward this way or that, right? So there's a electron density profile, and so the point is that this non-uniformity of gain medium, so in the diode laser there is a non-uniformity or spatially uneven density, non-uniformity in density of electrons. Okay, and so that then contributes to a line width of the light coming out. Okay, so that's the case in the diode laser, and in a solid state laser, such as a titanium sapphire laser, you can have a non-uniform dopant density of dopant concentration. Okay, so remember, what do I mean by that? You remember that in the titanium sapphire laser, and I'm going to forget right now, but what was the dopant in the titanium sapphire laser? I want to say, well, instead of TiSAF, let's do neodymium YAG, because I remember that one. Okay, so such as the ND YAG laser. Okay, and there the density of dopant concentration. What was the dopant? It was actually, I'm I'm going to forget even that. So the one that I do, which one do I remember right now? Which one had chromium as the? I think it was the ruby laser. Then I'm just gonna. I'll have to look up what the other ones were. And since time is at a premium, I don't want to stand around looking at my notes. I wasn't expecting I'll blank out on this. So let's do ruby. Such as, it's the most boring one of all those, but density of dopant concentration. So there it's the chromium ion. Chromium ion is the dopant, and that's the one that actually produces the lasing. Okay, so the chromium ion, it's distributed throughout the matrix of ruby, which is some aluminum garnet kind of thing. So it's distributed through, but it's an uneven distribution. All right, so it's not a homogeneous distribution. So non-uniform density of the dopant concentration also produces a line width to the laser. Okay, so these are actually examples of well, in any case. So you have the solid state lasers, diode lasers, gas lasers. In liquid lasers, it would be non-uniformities in the flow of the liquid that would create problems. Okay. So by problems, I mean it would contribute to the line width of the laser. And these would strike you as sort of technical things, right? I mean, there's nothing profound or fundamental about like Doppler broadening, or just the fact that there are collisions, or the fact that there is a non-uniformity in the distribution of ions or things. So if you were to somehow, let's say, try and get rid of many of these things, like for example in the gas laser, suppose you could really cool the atoms down and get rid of Doppler broadening, and you could arrange that there are very few collisions because they are so moving so slow, so there's no collisions. So if you were to make a laser out of like really slow atoms or something, well, but there is still a fundamental line broadening mechanism, which is so let me end this discussion here about the laser line width with fundamental contribution to laser line width, and that comes from the fact that light is emitted from atoms, and the thing about atoms is that if you have a ground state and the simplest atom, then you have an excited state, just two levels. Well, according to the Heisenberg uncertainty principle, these energy levels are not short is Hupp. According to the Hupp, these energy levels have a width. So if I look at the relative difference between them, then this excited state actually has a certain width, right? And so this delta E, as you know, simply cannot be determined to extreme accuracy. So then that means, and why is that? Because the Heisenberg uncertainty principle, just like delta X, delta P is always greater equal to H bar. Similarly, there's a similar relation between energy and time, and meaning that if your time period is short enough, then you can have a huge uncertainty in the energy. The shorter the time scale you look at, the larger the uncertainty in the energy. In fact, this is how people say that the Big Bang it allows for the Big Bang, that if you're for a really tiny amount of time interval, you can have a huge energy fluctuation. All right, and it's all allowed. So this delta E is the same one here, and the delta T has to do with the time involved in making the measurement, or it could be some other time scale. We don't have to go into that right now. But the point is that this delta E then means that the light that will be emitted from an atom, in the excited state as it jumps down to the ground state, there will be a certain delta nu to it, because there's a uncertainty in the energy. There will be a bandwidth to this light, and so there you go. I mean, that also contributes to the laser line width. Whoops, didn't mean to write on. So this this delta nu. One of the things that we were talking about here is that what's the experiment you wish to do? Is your laser line width narrow enough for the experiment you wish to do? Well, if we want to detect if we want to do atomic spectroscopy and do like really precise experiments with atoms, then the scale is actually set by this delta nu. All right, and so what I mean by that is that it turns out that this is it arises from the Hupp, and this is called the natural line width. Okay, and so for example, if you're wanting to study the rubidium atom, okay, which is what we will do in our lab, rubidium or cesium, but this is the one that we will do in the lab, then this delta nu that I just wrote down here, and so this is the natural line width, so let's call it delta nu natural. Delta nu natural is known, okay, and it's 6 megahertz. For sodium, this is 10 megahertz, okay, and so on. It's known for all the elements. So basically what this means is that in our case, we need our laser. I mean, if we're going to probe structure in the atom and hyperfine structure, if we wish to study hyperfine atomic structure, our delta nu L, okay, needs to be much smaller than the delta nu natural, okay. The Doppler broadening, for example, can be many gigahertz. So is the case for pressure broadening. It all depends. I mean, these numbers can vary widely, but this number, for example, it's quite a low number. It's a small number. All the other effects discussed above tend to be larger, okay. And this is the fundamental limitation, because you can't get around the HUP. But of course, we need to, our laser needs to be much less than that. And it's not that we're violating the HUP or anything. You always obey it, but you need to make it smaller than this, okay. So that's what sets our goal for us. So we will discuss the diode laser line width in the context of this requirement, okay. And so that's what we will do in the next video. We will discuss how much. What we will do is we will discuss how much this width is for the diode laser, all right, and then how can we reduce it to a much smaller number, all right, something much less than the 6 megahertz. Okay, well, that will be all in this one.